Here's solutions for a couple more free response questions. This is an oldie. This one's from, the 1980s or something. To dig way back for this. So let's see what we have. Two satellites of masses m and 3m, respectively, are in the same circular orbit around the Earth's center, but going opposite directions. The Earth has a mass of me and radius re. In this orbit, which has a radius of 2 re, satellites initially move at the same orbital speed, v sub 0, but in opposite directions. I want us to calculate the orbital speed. Now, you might just think you know what that is, and I bet you do, but they want us to calculate it here, so we have to show our work. The velocity in circular orbit comes from the assumption of circular orbits where the gravitational force would have to be what's providing that centripetal force. So let's see. It would be G. I'm going to be very careful here to use I'm not just going to write GMM over R squared. I'm going to try to use all the things that they used here, right? The way that they named things. Times, it doesn't really matter which satellite you use. I'll do the small satellite of mass m, because those are going to cancel, over the radius of the Earth. That's what they call that. Squared is equal to m. It's the satellite that's in orbit, so that's the small m. V sub 0 squared over r sub e. I have never gone off to do scoring of AP tests, so I don't know what they do if you don't name these the right things, if you don't follow what they did. But it could only be bad. It could be neutral or bad. So try to play along with the game. And I'm going to do this very lightly because I don't really want to disturb the work that I've done here. And I don't think there's another step that you need to show here. I think you can see clearly from this. You square root both sides. G, mass of the Earth, over radius of the Earth. And it's nice to know that ahead of time. You know you did it right. Alright, so assume the satellites collide head-on and stick together. In terms of v sub 0, find the speed v of the combination immediately after the collision. Alright, well, before the collision, let's say that this one's going in the positive. They're going opposite directions, right? So I know that the initial momentum will be equal to the final momentum. You could do this with angular momentum, but the r's just cancel out, so it turns out to be the same as this, mv equals mv. This is just a regular old collision. So let's see what we have here. So here I have initially I've got satellite of mass 3m with velocity v sub 0, and then I also have the other satellite of mass m, and that's minus because it's going the opposite direction, and then afterwards they stick together, so I have a mass of 4m stuck together times v, and they told me what to call that, v. Right? So that looks like I have here 3m minus m is 2m, v sub 0 is equal to 4m v, so v is equal to v sub 0 over 2 after they stick together. And I also know that v sub 0 is equal to this, but they said in terms of v sub 0. So there's that, a little bit of regular conservation of momentum. Then calculate the total mechanical energy of the system immediately after the collision in terms of G, M, ME, and RE. And assume that the gravitational potential energy of an object is defined to be 0 at an infinite distance from Earth. All that means is that I can use this. They're just covering their bases there. That just means that it's equal to negative GMM over R. That was the same assumption that we used to derive that. And this is on the equation sheet, so I don't have to do any calculus to derive that. I can just drop that. Oh, hold on a second. I'm just looking at something here and noticing that I made a mistake earlier. Because, sorry, I'm just looking back at this. I'm glad I caught this. The radius of this orbit is 2RE. So this would be GMEM over 2RE squared. This would be MV0. So this would be 2RE, and that would put a 2 here. So sorry about that. That's the radius of the orbit. It's not right at the Earth's surface. Sorry if you caught that before or was wondering, if you were wondering what was going on there. Okay, sorry about that. I'm glad that's fixed. And so here, the total mechanical energy of the system immediately after the collision, the total mechanical energy is equal to the sum of those two, gravitational potential and kinetic. So, gravitational potential is negative G, big M is mass of the Earth, little m is the mass of the two satellites stuck together, which is 4m, over r, and they're still, immediately after the collision, they're still at that distance of 2RE. Right? Plus, the kinetic energy is 1/2. Mass is the 4m, two satellites stuck together, times v squared. And it's this v, right? So that's v sub 0 over 2 squared. Now they asked for it in terms of G, M, ME, and RE, so that means I have to make this substitution back. And we'll try to clean that up. Let's see if I can do that without making any mistakes. So let's see what we got. Here I've got a 4 and a 2, so that will cancel to G, M, M. Over RE, right? Cancel. And then here, what do I have? I've got, this is going to be giving me a 4 on the bottom, so that 2 squared here will cancel with that, and this will be left there. I'll have a 1/2. And then I have an m, and then I have my v sub 0 squared, which is this, without the square root sign, times G M E for 2RE. So I have this over 4, and then I have 2 of these. Let's see. Getting a common denominator, we need a 4 on the bottom, so that's minus 8. No. Yes, need a 4 on the bottom, sorry. 8 GMEM over 4RE, right? 8 over 4, same as that 2 there, plus, and then here I have a GME small m over 4RE. So I have negative 8 of these plus 1 of these 4, so it's equal to negative 7 GMEM over 4RE. Cool. So that was, that was about algebra and being careful and stuff, but the key thing here is there's lots of points to be had here just from doing this right, and noting that this is not the velocity of circular orbit. When these things crash into each other after that, they're not going to be in a circular orbit anymore. They're not going fast enough, because they would have to have this velocity to be in circular orbit. They only have half that, so they ain't going to be in that orbit no more. Alright, that's that one. It's alright, 10 minutes. See if we can knock this one out in 10 minutes too. I think we can, because the first couple parts are super similar, almost identical in fact to stuff that we just did. Derive an expression for the orbital speed. So it's we have the distance from the center, so I know what it's going to be, right? It's going to be the square root of gm over r, but I need to derive that. So same thing, you got gravitational force, the centripetal force, and this is g m e times m over r1 squared. It's gravitational force, and centripetal force is m. They're currently calling this V1. I'm going to use all the same names, right? Squared over R1. So I'm going to delicately cancel so they can still see my work. And then they get that V1 is equal to the square root G ME over R1. Right? We've done that before. And if you wanted to get to Kepler's third law, if you want to get to the t squared r cubed relationship, then you just have to remember that this is also equal to 2 pi r over t. Then you do some squaring and keep going from there. Right? So, here they want the total energy of the satellite, assuming, here's this again, assuming gravitational potential energy to be 0 at an infinite distance from the center of the Earth. What does that mean? It just means that I can use this. That's what it means. It means that that is the correct expression. And they have to, they have to say that, because if they didn't, some kid, some smart aleck kid could come along and say, oh, well, I assumed that gravitational potential energy was 0 at, some other thing. And that would cause problems, because that answer could be considered right. So to cue you that you can use this, they have to say that. Anyway, if we know that, then the total energy, call that TE or ME for mechanical energy, is equal to gravitational plus kinetic. That's going to be worth at least a point right there, just saying that. And this is equal to negative G, mass of the Earth, times GMM over R, plus kinetic energy is 1/2 m V1 squared. They gave me plenty of room to do this. This is what the real AP test is going to look like. This is about how you're going to have about half a page per part to write things out. 1/2, geez, 1, that's a 1, 1/2 m, and then V1 squared is this squared, so that's G ME for R1. And then we know what this simplifies to, right? You could common denominator by putting a 2 there and there, and that simplifies to negative G ME times M over 2 R1. You can't, although this is a circular orbit, you can't drop the GMM over 2R. That's not one of the equations on the sheet, so you got to derive that. It's not, once you have this, you just have to square it and, it's right there. But you can't just drop that. All right, this is a little more interesting. So, those crafty College Board folks always looking for a way to work in some kind of twist. So this rocket is now going to be boosted out to here, and this is the force given by this equation here. Going to bump up to a radius, orbital radius of 2r1, twice as big as the previous one. And the component of the rocket's force parallel to the path, so in other words, the force always in the direction it's going, is this. where x is the variable distance traveled. And they want expression for work done. Well, I've got this force in terms of x, so I know that work is equal to the integral of force with respect to x. Right? And it's moving a total distance s. So I want that from 0. You can't leave this. You need numbers here or something here from 0 to s. You need to have the 0 to s. That is absolutely key. And then from here, it's a fairly easy calculus problem. You just have to manage these constants and stuff. So that means work is equal to, the force is this. So f sub 0 is a constant. I'm just going to move that outside the integral because it's just a number. And 1 minus x over s, which is just a number, that s is dx from 0 to s. The antiderivative of 1 is x. Antiderivative of x is x squared over 2. From 0 to s. Now when I plug in s, I get s minus s squared over 2s. When I plug in 0, I have x's here and here, so those all cancel out to 0. That's not always true, right? You do have to check, because it could be like a cosine of 0 or something, right? Those s's cancel, so I have s minus half an s. That's half an s. So that's equal to f sub 0 times s over 2. That's the total work done. Interesting. And it makes sense that the total work done would be a force times a distance, right? All right. Let's see what they're up to in part C. If the total distance s is equal to 3r1, derive an expression for f sub 0 in terms of me, r1, m, and fundamental constants as appropriate. Well, remember what work is. Or what work does, maybe. What work does is it changes the energy of a system. Work either increases or decreases the energy in a system. So work is equal to, sometimes we've written work is equal to the change in kinetic energy, but that's when there was no change in also in potential energy. Overall, in general, work is equal to the overall change in energy. So what's the change in energy? I know that work is equal to that, and the change in energy, that would be the total energy final minus total energy initial. And we actually found an expression for total energy here, didn't we? Didn't we? So we can use that. So the final total energy is negative g, mass of Earth, mass of satellite, over 2 times, the final r is the is this, right, the 2r1. The final is 2r1, and minus the initial. The initial is g, me is m, over 2 times the initial orbit, which was just r1. And now it's just a matter of simplifying and making some substitutions. They did tell me that s is equal to 3r1. So let's see if we can do that. So let's see, that's f of 0 times 3r1 over 2 equal to, and this is going to be positive here. It says a 4 on the bottom, so Sorry. Sneeze. Excuse me. So if I wanted to get the common denominator of a 4, I need to add an extra 2 top and bottom. So I'd have minus 1 of these plus 2 of these. So that would give me GMEM over 4R1. Let me just check my work there, make sure that that's right. My denominator here is 4R1, so I need the same denominator here, which means I need to multiply top and bottom of this by 2. So I have minus 1 of these GMMs, and then plus 2 of them. So yeah, that's right. Okay, and then solving for F sub 0, I get, well, let's see, I'm going to have to divide that down there. It's going to give me an R1 squared, 2 up top here, and that will cancel, give me a 2 on the bottom, and then, oh, that 3 is also going to go to the bottom, so I guess that's going to be a 6 down there. Right, when I multiply this by 2/3, be 2 over 12 or 1/6. So that's going to simplify to that. So the F sub 0 is 1/6 of the gravitational force.